Okay, so now I'd like to talk about induction on any recursive data type. So now I've got some new funny data type that I've defined here for a file. So a file is going to be a string of bits, and any file is either end, which means the file is ended, there's no more bits to look at, or there's a bit, which is a 1, followed by another file, so the rest of the file, or there's a bit and it's a 0, and then there's the rest of the file. So if we wanted to prove statements are true over files, how do we even do induction on that? We first need to define what it means to do induction on these things. So how we can define induction for files, so induction on files, is we need to figure out what the base case is going to be, and we need to figure out what the step cases are going to be. So for induction on files, well, the base case here is the file is ended. So we certainly need to prove for the empty file, the ended file, right? And now for the step case, what do I have to assume? Well, the idea is I want to assume it to be true for a file and then prove it to be true if the file's got a 1 added or a 0 added, because any file can be built out of smaller files with a 1 or a 0, right? So I want to prove the property true for end, and I want to prove the property true that for any file f, I assume it to be true for the file f, and then I prove it to be true for that file with a 1 added on the front, and I need to prove it to be true for that file with a 0 added on the front. Okay, so that's my step case, and if I can prove both these things, then I can prove for any file f the property holds for that file. Okay, so that's how we define induction for this particular data type. And you can define induction for other data types in a similar manner by like looking at the cases, where does it start, and given an arbitrary file, or given an arbitrary thing of that data type, how do I make it one bigger by adding more stuff to it? Okay, I've now defined a function on files called neg, short for bitwise negation. So what neg will do is it will take a file and will flip all the zeros to 1 and flip all the 1s to zeros. Let's have a look at the definition. Neg of the end of a file is just ended. We call that rule n1. Neg of bit 1 on some file f will return bit 0 and then negate the rest of the file by n2. And then neg bit 0f will flip the 0 to a 1 and then negate the rest of the file by n3. I would like to prove if I negate a file twice, I get back what I started with. Okay, so let's do a proof by induction. So the base case here is going to be the file is going to be ended. Okay, so I want to prove that if I negate the empty file twice, or the ended file twice, I get back the ended file. Okay, so let's start with the left-hand side. We have negate twice of the ended file, which by the definition of neg, if you negate the empty file, you get back the empty file. So we have neg of end by n1, and then we do that again to get end by n1 twice, which is equals the right-hand side. Okay, so the base case is pretty straightforward. Now we're going to prove for the step case. So let's have a look back at our definition for induction over files. For the step case, we assume it's true for some file, and then we're going to prove it's true if we take that file and add a 1 on the front, or if we add a 0 on the 1, or if we add a 0 on the front. So it can be true in both cases, okay? So we assume that negating a file twice doesn't change it, and then we have to prove two cases. So I'll prove this case first, and leave the other case to you as an exercise, because it's pretty much the same proof. So we have to prove that if you negate the file with the 1 bit added, bit 1f, it's the same as bit 1f. Okay, so let's prove it. We'll start with the left-hand side, which is the negation twice of bit 1f. Okay, what's that going to equal? Well, by the definition of negation, I take the 1 out, I flip it to a 0, and then I negate what's left over. So it's going to be neg of take the 1 out, flip it to a 0, and then negate what's left over by n2. Okay, so what is this equal to? Well, the negation of this whole thing, well, this is going to be some file, whatever it is. So if we look at the definition of negation, I can take the 0 out the front, flip it to a 1, and then negate what's left over. So we'll do that. So we have bit, the negation of a 0 is a 1, and then negate what's left over. So neg of f by n3. Okay. And now this part here looks like my inductive, I didn't label my inductive hypothesis. Oopsies. There we go. This is our inductive hypothesis. So I can replace this term here with the inductive hypothesis. This becomes bit 1 f by IH, which is what have I done? Oh no, that's fine. Yeah, we wanted to, well, sorry, I was looking over here. So we start with the left-hand side here. We negated twice. We got rid of our negations. We used our inductive hypothesis, and then we got this term over here. So this equals the right-hand side. All good. So we proved it for the base case. We assumed it's true for a file, and we proved it for, well, half of the cases. So now you go through and prove the other case, and once you've done that, it's proven for the step case. Therefore, we have, for all files f, if you negate the file twice, you're back what you started with. So, proof to reader, prove this case here. So, prove that if you negate the file twice and it starts with a 0, you get back what you started with. Bit 0 f. Okay, so do that as an exercise.